I'm going to give a primer on ambisonic technology. It's an old technology, but still very alive and current and getting more attention now with the VR 360 kind of current craze. So I'll give a little primer in, I guess I have 15 minutes. So what I love about ambisonics is it has an intermediate format, sort of like the DoMaster, where you can work independent of your reproduction stage. You don't have to worry about how many projectors are actually going out into the system. You create an intermediate format, and then you let the theater kind of decode it per projector. So ambisonics has a similar kind of infrastructure, and so I'm just going to talk about the technology essentially and some tools that allow us to go through this. So it is a complete surround sound technology. It has recording, encoding, which is the intermediate format, and a reproduction stage. It accurately produces 1, 2, or 3-dimensional sound fields. So it's extendable in the sense that you can use it for stereo, quadraphonic, 5.1, or a 32-dimensional, or I mean a 32 speaker array system. It can record rudimentary 3-dimensional sound fields using a single microphone. It's a 4-channel microphone, and we'll look at that a little later. Great. So like I mentioned, you can play back over any number of loudspeakers due to the intermediate format that they have. So this is unlike the current surround sound standards 5.1, which basically require you to compose your sound field or your sonic environment per speaker. So you have to have the idea of what the speaker setup is going to be like, and that's why they have the standard 5.1. The theory was developed by Michael Gerzon in the late 60s, so it's a very old technology. As a lot of, and it's been in continuous use at electroacoustic concert halls and that kind of thing for the last 50 years. So the intermediate format is what's known as B format. The encoding is lossless, meaning there is no quality loss, there's no compression involved. It's basically just straight like 44.1 sample rate or 48 or whatever sample rate you want to run. It's just a sort of a grouping system. So there's a thing called ordering in ambisonics. It's basically like a 1K DoMaster, 2K DoMaster, etc. So it refers to essentially the resolution, but we're not talking about pixels, we're talking about spatial resolution. Essentially how many speakers and how many channels you use to represent the sound field. So of course with any kind of resolution, you go higher, you get a better quality, you get more accurate representation. So the idea of the theory is eventually, as you keep going up and up in the number of channels, you basically recreate the physical wavefront. So it approaches a wave field synthesis, which is sort of the ultimate reproduction surround sound. So first order is kind of the basic. It's a 4-channel system representing 3 dimensions, which is sort of already better than a 5.1 system because you have the vertical, right? So the basics of the B format, or the intermediate representation of the sound field. The first channel is essentially for mono sound. And then the next 3 channels represent the spatial cues, the X, Y, Z kind of directionality of the sound field. So that's the way it's encoded. A single channel can be used for mono stereo, 2D, or single recording can be used for mono stereo, 2D surround, 3D surround, as well as binaural 3D stereo. So we use this a lot at IAI. We have a 15-channel system, and we do a lot of electroacoustic concerts and that kind of thing. So we often will play back over a 15-channel system in 3 dimensions, and then later we'll take that recording and master it down into a binaural set. Recently we've been experimenting with the GoPros. So we've been releasing on YouTube documentation of our events with a viewable 360 video and a binaural 3D immersion. So you can change the virtual mic setup after the recording has been made. So it's like being able to change the position of your camera after you've shot your footage, which is pretty awesome. As well as you can change sort of the number of virtual microphones. I said you can record it in one microphone, one 4-channel microphone. But when you decode it, and we'll talk about this a little more, you can change the position of the virtual microphones. So you say, I want this 4-channel single recording to represent 8 microphones in the field, which is a way to create surround sound technology. You can do that in post. So the basics of recording. This is sort of the theoretical explanation. And then, like I said, there is a single channel microphone that will do that. So basically, the idea is that you have sort of an extension of the mid-side technique. If you're not familiar with the mid-side technique, it's an omni microphone, meaning it records everywhere. And then you have a bidirectional microphone, which records the difference between the left and the right sound field. So you combine those together, and you can create a stereo pair. And then in post, you can change the stereo width, or you can adjust the left and right channels because you have this mathematically encoded. So ambisonics is basically an extension of the mid-side technique, but instead of just having a bidirectional mic and a mono, imagine that you have a bidirectional mic along the XYZ axes. So a homemade kind of microphone would look something like this. Pointing in a different direction. Imagine that the ones on the top and the bottom are rotated. It's hard to see in the picture. But this is the way it's commonly done, or sort of the right way to do it, because it is very hard to get those microphones in exact position. So just like the GoPro stuff, you kind of want all the cameras to be in the same position to avoid parallax. So you have the same kind of issues with ambisonics. If you use multiple microphones, you want them to be recorded from a single point, which is physically impossible, of course, to smash multiple microphones to exact same point. So there is another solution. It's to use multiple, what they call cardioid microphones. It's basically like a polar pattern, the shape of the heart. It records out in front and a little bit around, but not much behind you. And so you take 4 of those in a tetrahedral array, something that looks like that, of course, and you can then derive those X, Y, Z, and pressure channels that we just talked about. So the format that's recorded directly off this mic is what's called A format, which must be then encoded into B format. And a lot of these mics will kind of do this automatic for you. So this is one of the examples of these microphones, a commercial version. It's been around for quite a long time, used in very high-end production, like FIFA soccer games and Disney kind of events where you want to record this great ambient sound. But they are very expensive. This one is the SP200, I believe. These are what they call sound field microphones. It's F with a capital F, or field with a capital F. So this one basically is the cheaper version on the left, and then the more expensive one is something like, I think, $5,000. So it's not cheap, but it is a very high quality microphone. I've used it quite extensively. So this is sort of a cheaper version made made in New Jersey, handmade in New Jersey, but still works pretty well. It's called the Corsound Tetramic. It's about $1,000. So for $1,000, you can get pretty good 3-dimensional sound recordings over 4 channels. And then this is kind of a newer thing called the Brahma microphone, made in India. And these are also handmade, and basically what this is either a standalone mic like we just saw before, or he'll modify a portable recorder, the Zoom multi-channel recorder, and modify that with this microphone sitting on top of it, also for about $1,000, which is pretty cool, to have this 4-channel microphone in your back pocket, essentially. So just announced at, I think it was announced at CSS, but definitely this is from the CES demo recently. I think it seems like Sennheiser is finally getting into the action, the ambisonics. They're not quite saying what technology they're using, but it sure as heck looks like a ambisonic microphone to me. Has the cardioid capsules there, and they're calling it the Ambio. So we assume that is ambisonic technology there from Sennheiser. So 10 minutes. So Let's talk a bit about V format. So that is the encoded format. That is the DOM master of ambisonic technology, right? So we have 4 audio channels, like I said, 1, 2, 3, 4, or W, X, Y, and Z, as they're labeled here. The first channel is the overall pressure of the sound field, or the omnidirectional recording. And then you have essentially the directional movement across the XYZ axes. So it's the mathematics behind it is what's called spherical harmonics. And so basically it's a way to distribute the energy across a sphere, so looking something like that as in the visual form. So higher order ambisonics, like I said, spatial resolution. You go up in channels, you get more resolution, meaning you basically decompose that sphere that you're representing a little more. So the higher order ambisonics would look something like this. For 3D second order, 9 channels. For 3D third order, 16 channels. And these graphics are the visual representation of the spherical harmonics.
Does that mean you need 16 bytes?
So there isn't really a good solution for recording past first order right now. So you have to spatialize the mono sounds or stereo sounds. So exactly like I said, when you work in second or third order, you have to then basically compose or pan your sounds within the 3D space, because there isn't a very good way to record that higher order yet. So basically it's basically like working with a panner when you're using this, except you're working in 3 dimensions now along the XYZ axis, and you can place the sounds anywhere you want to in 3-dimensional space. The first order equations are actually very simple. It's not a very intensive process. It's basically just placing these items along the surface of a sphere. You can also simulate distance quite easily, which is often done. So moving towards the sound, the sound closer to you will increase the volume, etc. So the process of taking the brief format and then decoding into your speaker array is essentially done by the software, but the way it's done is basically it says how much energy is in that sound field that you want to present, and the decoder essentially says, given that speaker position, how much volume should I put within that particular speaker. So another way to look at the decoding process is a virtual microphone approach. So you can treat each speaker basically like a microphone. So, and you can change the polar pattern of those microphones. So this graphic represents a cardioid microphone, where the little thing that looks like a butt is basically no sound coming out. And you can basically say, I want less distribution on the left side, and I want more energy on the right side by changing the polar pattern, just like you would with changing the microphone. So this software, there's a lot of good software out there right now. Most of it's free, a lot of it's free, which is a good thing for us. And basically, this is a software I wrote a while back, I guess about 10 years ago now, and it's basically a panner and a decoder and all this kind of stuff, and it gives you a 3D graphics to kind of spatialize your sound. So if you imagine these little balls here are representations of sound. You can create these automation curves in 3 dimensions that they'll follow around just like you would create any kind of automation panning system. So nowadays, coming back to this sort of many years later after taking a break, I've started using the HOA library from CICM, and this basically does the same thing that my software was doing, but it's maintained by somebody else, so I could just get to use it and not write it. But sometimes I do plug in my visualization into this software, because after all, we are dealing only with XYZ coordinates. So the conversion from a graphics program like OpenGL or something is just a one-to-one translation of visual representation and sonic representation in 3 dimensions. So the HOI library is available for Macs. It's VST plugins, and it's available open frameworks and like a bunch of other stuff. So it's pretty good and pretty complete. This is, most people will use either Reaper because it has a very flexible multi-channel routing system, or Ardour. And I think Reaper is like $70 and Ardour is like, is free, yeah. So it's a very low-cost solution into 3-dimensional sound, Ambisonics. So it's been a long history of research, and these are some of the people I'd like to thank, so I thank you for your attention. Okay, we got 3 minutes if there's any questions. Yes.
To do a hemisphere typically, and get decent results, how many speakers would you recommend? Like sort of a minimal kit?
Uh-huh.
And then how crazy can you get?
Sure. For 3D at the bare minimum, you basically want to represent a cube, and that'll give you, if you're doing recording, that'll give you moderate results. But for 8 channels, 3 dimensions, you can get pretty good results. I think for a hemisphere, right now we're using a 15 speaker system, and we get decent coverage. But it's sort of like, it kind of depends on how big your hemisphere is and how close the speakers are. So it's kind of like, it's basically just similar to stereo, where if you were to separate them, you would eventually, you keep separating them more and more, you eventually find this hole in the middle. And that's basically what the center channel is kind of supposed to fill in the 5.1 system. But it kind of depends on your overall size.
Do you have to characterize the directional emission pattern from the speaker, whatever you call that? The
polar pattern?
Is that actually taken into account in the calculations?
Yes, it is. So you can, most of the coders will allow you to change essentially the polar pattern of each speaker. So the reason why you'd want to do that is maybe, you know how you have the sweet spot in any kind of surround sound system is exactly in the middle, just like the best seat in the dome is in the center, and you sort of get little off-axis parallax going on. So it's kind of the same thing with any kind of surround sound system in general, except maybe there's a few exceptions. But so you want to sometimes eliminate those artifacts by sitting more on the side. So you make adjustments essentially for optimizing the sweet spot or trying to broaden the sweet spot for a larger audience.
Thanks.
Mm-hmm.
If you were making smaller domes, like what kind of range of percentage of the surface would you perforate for sound transmission? Like kind of what's the lower limit and the upper limit for how much perforation?
You talking about like acoustic transparency of the surface, or?
Well, a lot of big domes, have holes in them, right, for ventilation and sound, maybe high frequencies. I just wondered what range of hole density you have. Some of the ones I've seen are like 22%, but I don't know what you're using in your dome, for example. Do you have an idea?
I don't know, like the density ratio or whatever. I'm not quite sure exactly. It is a perforated aluminum surface that you can broadcast, that we use at II, yeah. But
So the speakers are behind the
speakers
screen.
are behind the surface, yeah, which
Okay.
of course is important for
High
representing sound
frequencies.
over the surface of the sphere, yeah.
Yep.
Okay, thank you.